Hello, welcome. This is Physics 102A, the homework solutions for Chapter 10 on solids and fluids. Starting with number 15, aluminum's density is 2,700 kilograms per cubic meter. What is the radius of a solid aluminum sphere with mass of 10 kilograms? So it's giving the density, it's giving the mass. We want to know the size, particularly the radius. And so let's see how the size relates to density and mass. We have the equation density is mass over volume. Do the algebra, so volume is mass divided by density. Specifically, we want to know the radius, so let's take that volume down to the volume of a sphere is 4/3 pi r cubed, and then solve that for r, for radius. So we're going to multiply by 3/4, divide by pi, take the cube root, and so you should, through the algebra, get that the radius is the cube root of 3 times mass divided by 4 and density and pi. Make sure that it's all in MKS units, and yes, the density is in kilograms per cubic meters. Mass is in kilograms. By the way, if you have trouble on your calculator finding how to take the cube root, because some calculators, most calculators do not have a cube root key, and some of them, it's difficult. It takes a few steps to get to the cube root. So if that's the case for you, you can always put it to the exponent of 1/3. So cube root is the same as putting something to the 1/3 power. And when you do that, you should get 0.096 meters. It's a multiple choice question, and choice D is 9.6 centimeters. Number 25. If you boil away 1 liter of water, what volume of water vapor is produced at the temperature and pressure given in table 10.1? And as I look in table 10.1 in the book, it says that the density of water vapor at 1 atmosphere and 0 degrees Celsius is 0.804 kilograms per cubic meter. So we'll be using that. What mass is 1 liter of water is something we need to think about, how much mass we're dealing with. And so we can do that. Mass is density times volume, and we're just talking about liquid water here. So the density 1,000 kilograms per meter cubed times 1 liter, you should know, is 1,000th of a cubic meter. And so 1 liter is a kilogram of water. You think about these water bottles. A good sized water bottle is, sometimes it's 32 ounces, but that's about a liter, so that's a kilogram mass. All right, so now we're taking that mass and we're boiling it away. We're turning it into vapor, and we want to know what volume is it going to be. So volume is the mass divided by the density of vapor. So 1 kilogram that we figured out in the previous line divided by the density of 0.804 kilograms per cubic meter, and we get 1.244 cubic meters. So you think about that. It started as a liter of water, and now as vapor, it's increased in volume by actually greater than 1,200 times. It's now 1,244 liters, or 1.244 cubic meters. Now there's another way to solve that, and we can bypass this line where I found what the mass of a liter that we're dealing with is, and it's this. We can say, set up a ratio, the volume of the vapor divided by the volume of the water. And we're going to use the density equation. So volume is mass divided by density. So we can say the mass divided by the density of the vapor. Okay, that's the volume of the vapor. And then when we divide by the volume of the water, that's going to be dividing by mass over density of water. But we're dividing by a fraction, so we're going to multiply by its reciprocal, which means we're going to multiply by density of the water divided by mass. Because the mass is the same, those will divide out, and we're left with the density of the water over the density of the vapor. So now we can say we have, look on the left-hand side of this equation and the right-hand side. So the volume of vapor, divide by the volume of water, and let's multiply by volume of water. So volume of vapor is the volume of water, which is 1 liter, times the ratio of those densities, and you should get the same answer. Number 27, uranium depleted of its fissile isotope is used in armor-penetrating bullets because it's hard and dense. It's also mildly radioactive, making this a controversial issue. How many times heavier is a uranium bullet than a lead bullet of the same size and shape? All right, same size and shape, how much heavier? So we're looking at a ratio. What is the ratio of the weight of a uranium bullet over the weight of a lead bullet? And so the weight of uranium is mass of uranium times G, divide by the weight of the lead bullet, mass of lead times G. The G's divide out, and we're looking for a ratio of their masses. We'll use the density equation. If density is mass over volume, then mass is density times volume. So mass of uranium, we're going to call that density of uranium times volume. Mass of lead, we're going to call it density of lead times volume. And in this problem, they're the same volume, so those divide out. And we're left with that it's just the ratio of the densities. So the density of uranium, you can look it up in the table in the book, and that is 19.1 grams per cubic centimeter. Lead is 11.3 grams per cubic centimeter. So that ratio is 1.69. And we see if we've answered the question correctly. It says, how many times heavier is the uranium than the lead? So yes, that ratio answers the question, 1.69. Number 37, as we get into fluid pressure, it says if you use water instead of mercury in a barometer, what's the height of the water column when the pressure is 1 atmosphere? Is a water barometer practical? All right, we'll use this equation that pressure is rho GH, density times G times the height. We want to solve for the height, so it's pressure over rho times G, and we'll plug in pressure. We're looking at the air pressure of 1.013 times 10 to the 5th pascals. We're going to divide by the density of water, 1,000 kilograms per cubic meter. G is 9.8 newtons per kilogram, and the units are going to work out to be meters, and it's 10.34 meters. So if a barometer has water in it, if it has mercury in it, we're looking at a height of about 76 centimeters. If it has water in it, because of the lower density of water, it has to be very tall, so 10.34 meters. That is about the height of Porterville College's stadium. So it's a very large barometer. Is that practical? Well, it depends how much space you've got. Might not be practical to make a barometer that large. However, on the other side, it would have great accuracy just because it's so big, so you could get the markings on it the markings would show small changes in pressure. Number 41, what is the ocean depth at which a diver experiences a pressure of 3 atmospheres? So we'll use the equation we used in the previous problem, number 37, that the pressure from the water, notice I put a subscript of W there, is rho GH, and so H is the pressure from the water divided by rho G. Now, it's asking, what is the pressure that the diver experiences? What is the depth where the diver experiences 3 atmospheres? And it's being a little ambiguous. It's not saying whether that's a gauge pressure, meaning on top of the normal atmospheric pressure that the diver is used to in everyday life, or the total pressure. I'm going to interpret this question as meaning the total pressure. So the total pressure of 3 atmospheres is the 1 atmosphere pressure exerted by the air pushing down on the water. That's 1 atmosphere, plus an additional 2 atmospheres. So what we want to figure out using the equation that's on the top line is what depth of water is going to create a pressure of 2 atmospheres. So in the numerator, we've got 2 times 1.013 times 10 to the 5th pascals. We're going to divide by, now it says in the ocean, that is salt water. And so we can't just use 1,000 kilograms per cubic meter. 1030 is about right for salt water. And then G is 9.8, so we get 20.1 meters. So you go just 20 meters under the surface of the water, and you're experiencing 3 atmospheres of pressure. Number 44, a 3-meter deep swimming pool measures 25 by 15 meters. It's filled with fresh water. What force does the water exert on the bottom of the pool? Well, pressure is force divided by area, which means force is pressure times area. And the pressure exerted on the bottom of the pool is going to be P naught plus rho GH. Now, P naught is the pressure, the additional pressure just pushed on by the atmosphere, pushing down on the surface of the water, plus rho GH, which is the pressure contribution of the water itself. And then we're going to multiply by the area of the pool, its length times width. So you can plug in all those numbers. You can see all the values that I've plugged in. It's fresh water, so it's a density of 1,000 kilograms per cubic meter. And what we've got here in parentheses is the total pressure, that produced by air plus produced by the water itself, times the area of the pool, 375 meters squared, and we end up with 4.9 times 10 to the 7th newtons. Number 51, some buoyancy. A 70 kilogram parachutist whose density is 1050 kilograms per cubic meter is in free fall. Find the buoyancy force due to the air and compare with the parachutist's weight. All right, so normally we think of buoyancy as maybe something in a pool of water, but even the air around us, being a fluid, gives a buoyancy force. In fact, that is what makes helium balloons float. So there will be a small buoyancy force on the person, and let's see, the buoyancy force is, this is Archimedes' principle, it is the mass of the fluid that has been displaced by the body times g. So we're going to say it's the mass of air, and the mass of air is the density of air times the volume of the air that's been displaced. Now that volume of air, that V is doing double duty. Yes, it means volume of air, but in the next line, I'm going to call it the volume of the person's body, because that person's body, by being present, is displacing air. So in the line below, I'm thinking that V is the volume of the person's body, and that's the mass of the person's body divided by the density of the person's body. So here we have that the buoyancy force is the density of the air times mass of the body divided by density of the body times g. And we can plug in all those values, and it's very, very small, 0.84 newtons. So a small fraction of a pound. And then it says, now compare this with the person's weight. So buoyancy force divided by the weight of the person, which is the force of gravity. So 0.84 newtons over the person's weight, mass times g, and you get 0.0012. And so that's why we do not float in the air. There is a buoyancy force, but it's only about 1,000th of our weight. So fairly negligible. Number 52. A 2.5 gram penny with density 7140 kilograms per cubic meter is released just below the surface of a pool of water. What's the initial downward acceleration? All right, so picture this. You have a penny, you're at the surface of the pool, you let it go, and it's going to drop, but you know it's not going to drop in free fall. It's going to slowly drop to the ground. Or the bottom of the pool. Why does it slowly drop? Because yes, gravity is bringing it down, but buoyancy force is holding it up. And we want to know what is its initial downward acceleration. Certainly it's going to be smaller than 9.8 meters per second squared. First, we draw a force diagram. So buoyancy force up, the weight down. We'll use F equals ma. And we have, now notice what I've done here. I have called down the positive direction. That way I get a positive acceleration. So weight is positive minus buoyancy force, because I'm calling that the negative direction, equals mass times acceleration. And we have information on the mass. We have information on the density of a penny, on the density of water. We don't readily know the volume of a penny. Let's fill things in. Weight of the penny is mass times g. The buoyancy force is the density of the water times the volume displaced times g. That's Archimedes' principle right there. Equals mass times acceleration. And be careful in all these problems that you're distinguishing very often we're looking at the densities of two different substances. Maybe it's the object and the fluid. And make sure that you are distinguishing which density are we talking about. So remember Archimedes' principle, this bit where my red pointer is, says that it's the mass of the fluid that's been displaced. So it's the density of water times the volume. All right, so mass of the penny times G, that's the weight of the penny, minus density of the water times, and the for volume. Now I'm calling it, even though in the previous line it was the volume of the water displaced, I'm now suddenly calling it the volume of the penny because it's the same thing. The penny's volume is displacing that volume of water. So now is the volume of the penny, it's mass of the penny divided by density of the penny times G equals, and now MA. Well, we're talking about the acceleration of the penny, so it's the mass of the penny. And you notice that mass of the penny is a factor in every one of these terms, so we can just divide the entire equation by mass of the penny. And we no longer even have to think about the mass of the penny. It's irrelevant. So I'll clean this up, solving for acceleration. I can factor out G, and it becomes 1 minus density of the water over density of the penny. And then we plug in the values, and you should get 8.43 meters per second squared. Number 54, ice, which has a density of 931 kilograms per cubic meter, is floating in pure water. What fraction of the ice's volume is above the water's surface? Now, I derived in class how to get this. Can be a bit, it's not that long of a derivation, but it is much easier just to know the formula, and you can do this a lot easier that way. So here's the formula I derived in class, that the fraction that is submerged is equal to the ratio of the densities, the density of the object over the density of the fluid. And so we don't have to do any derivation. Let's just use this formula. And so the question is asking what fraction is above the water surface. Okay, so the fraction submerged is 931 divided by 1,000, 0.931. 93.1% is submerged. So the percent that's above water is just 100% minus that, or 6.9%. Number 55, a solid wood ball floats in pure water with exactly half its volume above the waterline. What is the wood's density? So half is above the waterline, half is submerged. So the fraction submerged is the object, the density of the object divided by density of the fluid. We want to know the density of the object, multiply both sides of this equation by density of the fluid. So it's going to be 1/2 of 1,000 because it's in water, pure water. So 500 kilograms per cubic meter. It's half the density of the water, and so half of it is submerged. Number 67 brings us into fluid motion. Water flows through a 2.25 centimeter diameter hose at 0.320 meters per second. Find A, the volume flow rate, and B, the speed of the water emerging from a 0.3 centimeter diameter nozzle. So when you see a question like this, be careful. It's giving the dimensions. Very often dimensions of something round are given as diameter, but very often in the formulas we use radius, so just be mindful of that. Well, the volume flow rate, which is Q, that's area times velocity. It's circular, so pi radius squared times velocity. So pi times, and we have 2.25 centimeter diameter, and we need that in meters, so 0.0225 meters, and to get the radius, divide that by 2 and square it, then multiply by the speed, 0.320 meters per second, and we get a volume flow rate of 1.272 times 10 to the negative 4 cubic meters per second. It's a very small number, but you think how much water a cubic meter is, and that this is just in 1 second. All right, so now it's asking for part B, what is the speed of the water emerging from a 0.3 centimeter diameter nozzle? The hose, it's just been restricted, the waterway, from 2.25 centimeters to 0.3 centimeters. So it's been restricted a whole lot, and so it's going to speed up. And let's use this, that the continuity equation says area 2 times speed 2 equals area 1 times speed 1. And then we can find speed 2 or velocity 2 in terms of the different radii or diameters and the original speed. And so we can say V2 is A1 over A2 times V1. Turn those areas into pi r squared. So pi r1 squared over pi r2 squared, the pi's divide out. And now we have r1 squared over r2 squared in parentheses. On the next line, let's just make that r1 over r2 and square it. And then, of course, times v1. Now, the easiest way to do this, you could type in the radii, and you can even leave it in terms of centimeters, because as long as they're consistent units, the centimeters or whatever the units are just going to divide out. But something even easier is, let's not even bother to compute the radii. I know it's just a matter of dividing by 2. You could also use diameters because you're looking at the ratio. The ratio of the radii is the same as the ratio of their diameters. And to show that, I've just doubled, put a 2 in the numerator, 2 in the denominator. Now it's the diameters. So whether you wanted to plug in the radii or the diameters, it's going to be the same result. I've chosen to plug in the diameters, the ratio squared times 0.32, and we get 18 meters per second. By the way, you can check that by applying, this is our V2, and you were given R2, and you should be able to come back up here to the top and do the new area times the new velocity, figure out the volume flow rate, and it should be the same result as we got here in part A, because the continuity equation says the volume flow rate is constant. Number 70. Water flows through a 1.2 centimeter diameter pipe into a 250 liter bathtub, which it fills in 6 minutes. What is the speed of the water in the pipe? This is going to use the volume flow rate, but looking at it another way, we're given the diameter is 1.2 centimeters for the pipe. I've just gotten the radius 0.6 centimeters. We are given the volume flow rate. It's not in MKS units, but it's giving it to us. It's a volume per time. So 250 liters over 6 minutes. And we want to find the speed. So let's find the volume flow rate. Let's get that in MKS units. So 250 liters over 6 minutes. We want that in cubic meters per second. So 1 cubic meter is 1,000 liters. 1 minute is 60 seconds. You do that conversion and you get a volume flow rate of 6.94 times 10 to the negative 4 cubic meters per second. Now, we want to find the velocity. So we'll use the volume flow rate is area times velocity. Solve that for velocity. It's volume flow rate over area. And this is why up here we solve for volume flow rate. Area of the pipe is, it's circular, so it's pi r squared. And so we plug in those values and we get 6.14 meters per second. Now we can check our answer this way. Let's find the volume flow rate. So we're going to kind of use the answer we got, work it backwards to see if it gives us the original information. So volume flow rate is area times velocity, which is pi r squared times velocity. Pi, there's your radius, make sure it's in meters, times the velocity. Up above, I rounded off to 6.14, but let's use the full digits the calculator gave me, 6.140237. And that comes out to be the volume flow rate that I got up above. So that's good. That gives me confidence. But let's actually get this in terms of the original information in the problem. Let's get this in liters per minute. There are 1,000 liters per cubic meter, so I'll multiply by 1,000. There are 60 seconds in a minute, so I'll do 60 seconds over a minute, and it gives me 41.6 repeating liters per minute. And then I think, well, this was 6 minutes of filling the tub. And so multiply that by 6 and you get the 250 liters that the original information gave. Number 75. On a stormy day, a wind of 90 kilometers per hour blows parallel to the surface of the picture window with area 4.5 meters squared. What are the magnitude and direction of the force on the window? All right, here's my window, inside the house and outside the house. Pressure 1, pressure 2, and normally when we think about a window in the air, it's the same pressure on both sides, but there's a wind that's going to blow parallel. Notice the wind doesn't push in. It's not blowing into the window, but it's just blowing across the window. But that speed of the air is going to change the pressure. And we want to know the magnitude and direction of the force on the window. All right, so the net force is going to be F1 minus F2. I'm calling to the right the positive direction, so the pressure pushing from inside is F1 minus the pressure from outside F2. So we have P1 area minus P2 area. And it's the same area of the same window, so we're going to get area is P1 minus P2. Now we're going to use Bernoulli's equation. We have P1 plus 1/2 rho V1 squared plus rho G Y1 equals P2 plus 1/2 rho V2 squared plus rho G Y2. Those are the same. The last terms in those expressions are the same. Rho G Y1, rho G Y2, not really a difference there. They're the same thing, so we're just going to subtract them away. We want P1 minus P2 because that's what we had up here. We want to find out what that is. And so we have equals 1/2 rho V2 squared minus 1/2 rho V1 squared. And V1, there is no speed of the wind inside the house. That just goes to 0. So we have P1 minus P2 is, and it reduces down to 1/2 rho times V2 squared. So we have 1/2 times the density of the air times the speed of the wind squared. And when you plug those in, you get the difference in pressure between pressure inside and pressure outside, 400 pascals. Then we're going to come way up here. It was area times the difference of pressures. So the net force is the area times the difference in pressures, 4.5 meters squared times 400 pascals, and we get 800 newtons. And notice that that's in the positive direction, outwards. So with the wind blowing, the window will actually blow outwards. 1,800 newtons, that's about 400 pounds. So that's a considerably large force against a window. And that is the end of the Chapter 10 homework. Have a great day.